Peace. Straight into the intermediate axis and wingnuts. If you have that special kind of bolt nut in space and you spin it round, it spins, it spins, it spins, and then it flips, and it spins and spins and spins, and then it flips. Well, I can explain to you really why the thing that's spinning in space is going to flip once. And that's to do with it takes the least amount of work to flip along that axis than to do anything else. What's weird is that it keeps on flipping, and we're going to think about it in terms of electronic orbital spinning. Okay, so the basic premise that if you have a wing nut that's spinning in space, it's going to keep on spinning and then it's going to flip. Why does it do that one flip? And sometimes this is called the tennis racket theorem, because you see the same thing with a tennis racket, that if you try and throw a tennis racket so that its big flappy thing is here, and you throw it up in the air, even with a really rigid thumb, you're going to see the tennis racket flip over, and the way that the tennis racket flips is always going to be predictable. Okay, if we imagine that there's an object, it's a sphere, and it needs to spin around in a circle, or it's got a heaviest point on the edge, we'll assume. And if I want to spin the sphere in any direction, the sphere has to go around, and it takes the same amount of work to carry something as heavy as the extra weight around the sphere in any way. But if I have another point on the sphere that also weighs something, then I get the best possible efficiency by trying to line up the heavy thing and, say, the less heavy thing as close to opposite as I can around my direction of spinning, so that the least heavy weight by itself exists that we need to carve around the circle, and also it's most counteracted by the other thing. So, given an object that's irregular, it always sorts itself out to basically find the heaviest weight on one side and the lightest weight on the other side around some axis, and then spins around that axis so that, uh, well, all the vectors of rotational momentum are resolved in the least amount of work. That's very theoretical. It doesn't explain how it happens, but that's what happens. That um, given a spinning object, it wants to take the course that carries the least mass through the least amount of space. That's kind of obvious. That's why, at a certain point, when you're spinning, when you've got your spinning wing nut in space, it's going to eventually start to decay in its spin, that it's going to lose some heat. That can't affect it all in the same way at every point. As soon as there's something, some path along the spin which seems like a heaviest moment, there's got to be a new heaviest point that wants to resolve with the lightest point. And always we're going to find that it flips along this same dimension, because the extra wobbliness always happens at the heaviest end, and the lightest way to resolve it is always hitting by turning around a rotational axis that's between the heaviest bit and the lightest bit. What this doesn't explain at all, and what the intermediate axis theorem by itself doesn't entirely seem to explain, is why then the wing nut keeps on spinning. That it spins, it spins, it spins, it flips over. You're like, okay, well, then it's done. Then it's gone to its ground state. And there we've invoked that that was the least amount of work it took to spin everything to that point. So why is it going to go now spin again? I want to think of it in terms of, we've got within the wing nut a whole load of atoms that they've got electrons that spin around them in regular patterns. And when we spin the whole wing nut, we're going to imagine that those orbital paths stay with the same relations to each other as the whole thing spins around when you spin its context. As that happens, we've got two dimensions of spin which are always being reinforced. That there's a spin that the whole context has, which is 2 dimensions. And we've got that spin being reinforced by the things that they're always going to find it maybe a little bit easier to progress along those dimensions because the whole thing is spinning. In fact, they would have to work harder to not find it easier. Now, it appears that when we take a whole object, the individual orbital paths of the electrons mostly cancel out over the whole system, that you don't get resultant charge from these guys working individually because there's billions of them, and if it were going to be that they're going to produce any work by like rubbing fields the wrong way, well, they just won't, and the system relies that it's remains at its ground state. However, when you're spinning the thing, then it is still the case that there's a part of each electronic orbital's trajectory that you don't have to move within your orbital to reach the next point within your general course. So when the wingnut is spinning like this, we're saying then that all of the electrons in their orbitals are somehow reinforced along this dimension. This would mean anywhere along here, it would literally be heavier. And so they want to flip around. And that it takes a little while to build up that heaviness. What are we building up the heaviness from? From constantly reinforcing this electronic path by spinning the whole thing, and we needed to just spin a bit of it. So we get a little bit more effective weight that always builds up and makes this end of the wingnut heavier so it can all flip. It happens most here at the heaviest end because there's more stuff being reinforced. And at that moment, there's enough extra weight as a function of that extra reinforced energy is going to flip. And that's why it will continue to flip, because you keep on building weight here. Now we've described the same thing as it loses heat and it gains weight. Loses heat, we mean well, that the electronic orbital states of the atoms involved should all become less chaotic, if we mean heat. But where it becomes less chaotic is very chaotic. Yeah. Yeah. You know that it's going to dissipate some heat, but you really can't tell from exactly which point it's going to dissipate heat, which means that the overall function of the bundle of atoms together is going to be hard to predict, even though individual bits are going to be easy to predict compared to what they're nearby. The other way we've explained that same thing is to say that in certain positions, there's more reinforcement, there's more stipulation for order, but it can't be heat. We've definitely got an effective mass there kind of coming out of nothing, which is cool. And it definitely seems to ping away once the thing turns around. It's like a little reservoir of potential that eventually hits a bit of mass and then flings around. That's awesome. the reservoir of potential is what we're calling the reinforced dimension of spin. The more reinforced it is, the more that potential gets to, the closer it gets to that point where it goes, hey, it's just easier for me to, instead of carrying this big heavy weight along this way, go, whoa, because it's a shorter distance. But that weight, it just appears. It appears exactly along the dimension, and like arbitrarily, that where that weight is with respect to the spinning thing doesn't matter. It's not a weight that needs to have a particular location, because it's going to behave, the whole system's going to behave pretty much the same anywhere. Is that true? Yeah, when I flip over that other axis, it doesn't matter what was in place where with respect to that axis. The axis is always going to be chosen between the heaviest point and the lightest point, but the lightest points are all pretty much the same, the heaviest points are all pretty much the same. And this function of reinforcement, we're waiting for it to get to a discrete, now it seems like I have weight over here, value, which it gets to in increments which are necessarily really hard to compare to that. Now I have a weight value. The now I have a weight value is only effective within the context of this absolutely spinning thing. And it just seems to not matter really where it is within that spinning thing. It's just there's weight attributed somewhere within this spinning plane. That's going to flip it over. I don't know if it's related, but if you have a circle and you just lay it on the floor, it could equally roll either way, say. But if you pull it out and let it go from being circly to ovaloid, then it becomes what I call like a highly decisive state, that it's more likely to fall over immediately. And if you do the same kind of transformation from anywhere on the circle further down the way, then it's way more likely that it's going to tip over. But if you do it sort of towards the top, if I did it right at the top, then it would be highly decisive, but not about which. It would just want to fall over one way. If for some reason you were seeing circles coming into being as first they're straight lines and then they kind of widen out, then they start at that pivot where it's in the most volatile, undecided state where it needs to decide something. What does that give us? We're now thinking in 2D about this thing that was about 3D vectors. Intermediate axis theorem, gaining a little bit of mass by spinning. If that's the case, we should be able to pin a bit more on Yang-Mills, because we're talking about purely electronic mass and saying that that's an evidence of it. Cool. Does the circle thing help? Well, assuming an atom is surrounded by other atoms, they've all got these orbitals going on, and the shape of my orbital path does matter with respect to the other orbitals going on, and there is this kind of, if my orbital is long and stretchy, it's just more prone to fall over. means that if my individual atom is excited, so that it is more pointy ovally, yeah, something down here is going to disproportionately affect the end of it, and you've got more leverage, you've got more rotational impetus just because I got longer and stretchier. What's going to happen then if, well, also being longer and stretchier, then when I have that rotational impetus, I affect more stuff over here to try and push it along. So that would be why heat dissipates from one excited electron or one excited atom. If I have one excited atom, or if I have an atom at ground state, and then I force some new electricity into it and speed up that electron in there, I figure I've always got to do that from a certain trajectory. I've got to be somewhere in relation to it. And also electricity seems to work in this kind of dynamic. We want it to be in quite 2D reality, that I come in and I'm just a single line with a location, and I poke the orbital shell. Still, along that orbital shell, it should elongate as the thing is going faster. Why? Because it's going to keep constant how much energy it requires to go around the whole thing. But you sped it up so that you don't require that, or you can see it as you squished time space down a little bit. Time space we'll get to. Right, so if I have a ground state atom, I ping any extra electricity into it. It has to be from a trajectory. It's going to make some kind of Ripley cause and effect thing. Now, we're imagining that it's really easy for this thing to go laterally, but the one thing an electron doesn't want to do is go in or out ground states, at least not without having made a big course around the outside. So there's going to be one dimension that has something special about it. So that we can traverse a whole atom's width curve ways, but still transmit information at the speed of light linearly, it can be that, very much like the mesh nets thing, where if I poke you here, nothing's allowed to go in, so it just ripples around the side. And if I stood at any point and like figured out where the ripple was, I wouldn't know anything about that event until the whole thing had come around to the other side. Because you need to know where this thing is going to end up to know where it began. So that is my model of the atom that you see an electron spinning around the sides at the speed of light while carrying information at the speed of light or close to it, but you don't stand at any point in between and see all the information because it's all rippling around the edges, and the amount of information that gets passed through a distance is kind of defeated by the fact that you're sending it through a sphere and not a line. So you've got partial information about the event going around the sites. Quicker than the speed of light. If it takes speed of light time to traverse sort of the diameter of an atom, but all the information goes around the sides, going a bit faster, being more constrained, but also never adding up to the full information. I think that that happens, and then at least there's a way to see the path that the orbital takes along that route as being elongated, that there's more something in there. And everything around would see that path as elongated, like tight. You would see that a ripple has gone through, you just wouldn't see what the ripple adds up to. If this keeps happening, if you had a plane filled of circles all touching each other, and then one of them you just started pulling, even gently, and putting it next to each other, whilst all of the other ones have this constant behavior that they're pushing out against all the others, you would make just a tiny little bit of disturbance somewhere and, disturb lots of things. It seems like when we have these circles, it's going to decay like a wave that say I do deform one of these circles a little bit, and then I let it go back. It's not just going to fall to its most circular state immediately, perhaps, probably, but it will go and then land there. When things do this, it is a process where specifically the minimal stress is attributed at any particular point. I suppose you could call it dissipative. So what would it do if that's what we've predicted? We pull out a circle, everything in all directions is pushing against it. And the easiest things to push against proportionately are the two outtiest points. So the two outtiest points want to be squished back in together. The force we squish that back together with, if all the forces are proportionate with distance, that's going to have a bigger push on it than the sides had, where the sides were furthest away from the things that were being pushed, as a case of being elongated. So if I take a time frame of like one moment and just see where's everyone pushing at this one moment, I see a lot of vectors pushing on the elongated edges and fewer vectors pushing the middle. So I just let that snapshot resolve. I let those vectors resolve, and I see a relatively big push kicked out here and a relatively small push here. Is that enough? We need to, I don't know if we need to imagine that the circle has like tension to its skin to be able to imagine that, okay, well, if we pushed it in relatively a lot here and relatively little here, oh, I can cancel out those vectors and cancel out those vectors and see that there's a net effect that pushes out the center, the sides which were depleted. Yeah, really? They all the vectors cancel out, but they cancel out this way the quickest. The two vectors at the elongated ends, they push against each other, they have some intersection. These ones, they push against each other, they have least intersection. And so whilst the force was equal in all directions, here most of the movement force is cancelled out, whereas here less of it is, which is the same as the sides swelling. An orbital path in 2D to behave once one of the things in that plane had become disturbed, that you get this elongation, and it means it's really prone to spin in any direction. That's what it would really want to do, that if you had that and you had the leverage is best here and here. And in fact, it would want to spin like as a function of how chaotic everything is. If everything was perfectly balanced everywhere, then these little more and more tenuous, highly decidable, elongated ovaloids, well, they've got equal forces on this one and this one, even when it's elongated, so it doesn't need to spin. But if there's anything different at all, and it's checking over here and it's checking over here, it should spin very quickly the whole context. And it's very much like the, I mean, subhanAllah, it's exactly like the intermediate axis theorem, but in 2D, where you've got the lightest bit, which is the thinned out sides, and the heaviest bit, the elongated ends. And what happens there, well, instead of flipping, you fill in more of the thing here, which is what you'd get if you span it and it was centripetal. But maybe that is a useful insight. Is there anything more we can say on the intermediate axis theorem? I like the explanation that the shortest route to spin an irregular heavy object is the one which takes the most heavy on the opposite of the lightest, and that's going to require the less momentum to move all the objects around. And also, the extra flip of the wing nut in space is a result of this like radial weight that is the reinforcement of the spinning electrons within their orbital that just eventually adds up to something that is effectively indistinguishable from weight, and it flips over. We don't really have why something spinning is like weight. Or we could think about magnetism within this thing, that if I've got electrons spinning all within their orbital circuit, then there's going to be a little bit of electricity that they make, probably, and that electricity usually sorts itself out when the thing is stable. There can never be too much of it anywhere because it's all going to dissipate. But when I spin the whole thing on two axes, one linear axis, one rotational axis, I'm thinking about the two planes here. When you spin it like that, you get a plane where that dissipate effect that always happens just needs to work harder to dissipate all the microelectricity between the atoms. In general, this is going to want to cancel itself out. That an atom next to another atom, they're both creating a little electronic field just by having an electron spinning around in a circle, which means that two of them next to each other are going to create just the right equilibrium to not really affect anything else outside. But if they're spinning around all together in a circle, whatever nature effect, whatever science was there to spread out all of that extra charge equally, there's one dimension that is way harder to do that in. We're saying that has the effect of mass. So mass is just charges lined up within this picture, which seems good. Might explain why, like, everything was orbiting something seems spin. That seems like a function of like how well it can communicate between them, that they're far apart. If you have the sun and you have an asteroid and the asteroid is spinning, I think that if you slow down the spin, the asteroid has to fall into the sun, just free fall proportionate to how much you slowed it down. Thank you. Let's see if this is an emergency. Okay. Not fun, but it's an not an emergency. We've got spinning that has like a generalized weight, that we're quite keen on the fact that this weight doesn't have a particular location. Maybe it will for like an instant before it spins across the intermediate axis, but this reinforcement effect is happening everywhere. It'd be really interesting to think about, well, we've got some extra mass, so we say, that exists everywhere around it. A circle, or a path through which it's easier for electrons to complete their orbits. They're already good on how to complete their orbits. They've got enough of that already. And so when you make it easier for them, in effect, it has to release some capacity of spin that it had and let that go somewhere else. The one thing you know about letting it go somewhere else is that it can't go in the same direction. Therefore, it goes out perpendicular to everything. What goes out perpendicular to everything? Because it's extra easy for me to spin in this direction, when I'm spinning in this direction, the stuff that's nearby me that isn't spinning in that direction and doesn't find it extra easy is like, wow, that's a lot of spinning in that direction. And that's all the stuff that's perpendicular to me. And that stuff all has some kind of stress contingent upon it that, well, I thought time was moving this fast, but it's going way quicker for you. What am I going to do about passing you pieces of information and telling you about cause and effect? This stress should be a stress on space-time. I've got these two things that are next to each other, and they're supposed to behave in the same way, but this one is way more excited than this one. so in the future, we know something is going to resolve and the two states are going to come closer together. I think it's just as good to say there's a stress on space-time between the two. There wants one thing to speed up and one thing to slow down. Does it ever get its way? Well, yeah, that stress follows those things around no matter where they go within this local context. And eventually gets its way. But what was that process? That was a process that we were describing elsewhere of the elongated things hit into more circular things and give it exactly the right kind of forces to make it end up looking like a circle. Also, the amount that we hit in the elongated ends is more than the amount that we hit in the sides, and so we expect it to contract a little bit, which would force it out this way. And you would find that at each point on the circle, to return to its ground state, had acted as similarly to everything else around the circle as it could. The responsibility of changing shape is equally distributed everywhere. Now, it's not a responsibility, it's the effect of all of these things we're imagining in a 2D plane just pushing against a circle which had become elongated. We would imagine straight away from that kind of thing. Also, if there wasn't spin rotationally on those circles to begin with, after you had pulled one out and seen the ends pinged about, you kind of would end up with a rotation of spin, or a dimension of spin within the 2D thing as a result of that ever having happened. Which you could then transfer and make everything in the system rotationally spin in a way that every other interaction in the system that we've described so far doesn't acknowledge, doesn't care about, doesn't take pictures of, can't measure. But whilst we're imagining all the other kind of vectors that can be there on a 2D plane of circles, none of them were spinning, they were just pointing in relation to fields, so they could spin, and like all of the rest of the physics stays the same, except there's this new process going on, more energy that you wouldn't be able to see if you were just logging what happens to the circly things which push each other. I guess that's what I mean by a proton. I do, but what I'm interested in now is to say, well, why is there a neutron as well? I know I believe that the neutron is like a proton that goes at 90 degrees to the proton. Or something like that. Also, that when the electron first carves out the right type of path to do an orbital, it's like a self-perpetuating loop, that it's the most efficient path it could possibly go through. And it effectively bumps itself on the butt so that the electron can keep spinning around the same path. I think that whilst it does that, it creates like a vortex on the inside of it. Oh, we've got some good math on this, where, yeah, inside of it is being acted upon kind of hyper finitely within our math. Cool. And so we're imagining that now this new artifact of space comes that you'd never seen before because you never had quite this force on it. But now this electron is spinning in the tightest path that it can to do a sphere. And at the middle, there's this point that becomes most stirred. And it's like it ties a knot in space-time and makes it into a proton. And then having tied that knot, the equal and opposite reaction of doing that to that bit of space is to make a neutron, which is pretty similar, but also twisted in a different direction. It sounds really good, but we missed the bit in the middle that we wanted to return to. And say, well, why would having 2D spinning circles produce that kind of thing? They would certainly make a new salient point if we had all these circles and they just exist as their edges, and we pull one and it starts being beaten about, and we know that it's going to resolve into spinning as a 2D thing. It's going to have this new salient point, which really wasn't there before at the center of the circle. There was nothing too special about the center of the circle until everything was spinning around it. Now everything is spinning around it. The point has this new behavior and perhaps this new agnosis that we wanted the electron to be born when, if you imagine light just somehow made a curl around one single point. If you're standing in that point and light hasn't traveled any time from its own perspective as you stand in the middle of it, and then your only perspective about time is to ask this piece of light, which isn't changing time as it goes through this minimal circle, then that speck in the inside, you're like, what time is it? And everywhere around you seems to be in the same time. Therefore you spin, and you spin with this kind of spin that doesn't cost any energy, because all you're doing is not knowing where the next point is. And as a cost of this not knowing, there's some pretty reasonable questions that you can ask about an electron that you can't know because it doesn't know itself, because it doesn't have well, at that moment where it's born, an indication of where time is next. So we want one of those, and then we're saying that the proton is a similar thing when you get up to 3D space, that now you've got this little guy that can spin, it can move in an extra dimension than light can. Or if you spin it this same old way that light used to spin, well, now it's spinning like this way, so it's going to go. Ooh. We like those, and we like the fact particularly that if you do this, there are some intervals where if I'm spinning around this way, I can either have a regular period and keep on landing on the same points that I had already traced, or I can have a transcendental period and never ever return to the same point that I've been on. If you just have systems of like, well, charge, and they're allowed to have certain frequency points where they intersect, and you get a difference. You get the difference between the type of function, even if they start the same way or they're defined the same way, they're made out of the same kind of shapes. You get a difference really clearly between, like, I can traverse a circle in 6 steps, or there's no amount of steps that I can take to traverse a circle and land at the same point where I began. So all you need is like the most basic definition of a wave, and you have a lot of capacity for making different kinds of shapes out of it. We have explained why the proton, yeah. Because if this wingnut is spinning around and we're saying that the reinforced dimensions, that's what makes it heavier. But that is the same as what we described for how the proton comes about, that you've got an electron spinning around and it makes that thing heavier. So we've got a prediction to make then that it flips at the time when this overall spinning, which is going to be, a really small spin compared to how fast the individual things are spinning, but with very many of them all reinforcing by that small amount, and we want to make it so that it's equal to, I guess, the first weight that you can get to that is bigger than an electron within this system. And it would be the case that the middle of that is where the mass went. But in this case, we're only moving around on one dimension, so we don't get a whole proton. We just get like a third of a weight, a glimpse of something. If we were to construct a system where we could spin that much, on 3 different rotational vectors, we would get a proton on the middle, in the middle, so we're saying. But in this case, we don't. We just get some extra weight, which is some extra work that time-space is going to have to do, which is the same as there's this point in the middle, which just is particularly dissimilar to the points around it. That's all we need for there to be the special need to dissipate here, and that special point, that's going to be the case because this point in the middle is affected, by every spin thing that's anywhere. It's the middle where everything over intersects. So that point is going to be very different to the points nearby. And then how it resolves, how it dissipates, is a function of the electron spinning around the orbital. Can't tell an electron where it is or what it's doing unless they're both close to each other. So dissipating energy throughout this atomic system has something to do with how long it takes for an electron to spin around the whole course, because you can't tell like infinitely many points around you all at the same time anything. You need to wait until the electron goes through its course and then tells things along the way what is our energy state to compare them. And once they hit, it takes like a subliminal amount of time to resolve the two things, because even this moment of them touching isn't a moment that we can measure, because all of the information is there. All of the information is when they click. Now, what are we saying information is? This extra charge that this one electron has in the orbital, which is a bit of stress on the orbital in one of its 3 dimensions. I mean, the stress on space-time is the fact that it's gonna move a bit quicker through its orbital throughout this period. Why is that? Because it just had an impetus. What does the impetus do? Passes electricity into that orbital. There we go. We're just dissipating electricity. But we've got this technique that you can only dissipate to the next orbital for this special case of electricity, where the electron goes around in its highly charged state, finds another atom that it's close to, and then pours out some of it there. Now, as it's all going kind of faster than the speed of light and particularly doesn't care about directions and particular locations, if I hit an atom here, we're saying that the main consequence is going to be found over here, but there's going to be parts of that information scattered all around that don't add up to the whole event. Is there any reason then for them to wait? Or can... Seems like everyone who's every circle that's adjacent when we're trying to dissipate some energy, maybe they can all know at the same time. Why do I think that? I imagine you've got a circuit and you've got 4 points on it where you could break it or you could join up to something else and let current flow over there. If I break it over here, you know that already just by turning on the switch here. You're going to know that in the amount of time it takes an electron to go around. But actually, you're going to know that quicker than the time it takes the electron to go around. No, because you wouldn't be expecting any return result until it got you over here. But what if you heard an unexpected return result that's, I sent my electron over here and there was nowhere for it to go, so it came back. Half of the circle, I can find out if there's an obstruction quicker than going around the whole route. What does that do? It allows me to start dissipating the energy that I need to dissipate everywhere across half of the points of the circle immediately before having to wait. So I would know where everyone is. I mean, it would get harder to measure by the system we've just described if there were more than one outlet on the half of the circle you've described. You wouldn't get any information about that. What is this half a circle? This half a circle is if you were looking at an electronic orbital pattern around an atom and then you just managed to elongate it somewhere by any means, you would see the elongation want to resolve and turn it back into a perfectly circular orbital path. The only way it can do that is by being the electron affecting what are effectively magnetic fields, the fields that are perpendicular to its course. These fields, it can only interact with, we're saying, by being there. But before it is there, it's going to travel through some other points which could all dissipate and kind of affect this bit before the information about that had happened. Why? Because stuff is complicated down here, and that's sort of what it looks like. That you could have simultaneously discharging orbitals over half of the atom or something like this, because how half of the atom behaves is quite different to how the other half of the atom behaves in terms of sending out an electron and then seeing if it returns in just the amount of time it takes to do an orbit, or does it take longer than that? Or does it take shorter than that? Those are the questions you can ask in the front half or the nearest half of your orbital, and you've got this other half, which has to behave a little bit differently. That difference in timing could be enough to make all the differences in timing, if we needed it to be, that the electron has a sense of near and far. Once you get out and you get to the equator, you said that maybe you can dissipate all the energy you need over on this side across the equator. Unless you're adding more information somewhere ex nihilo, if that has happened, then the other side of the sphere would be most likely to try and dissipate in the same sort of shape as it did this way. Otherwise, you got to create a new function of how that's going to happen. And if we're saying that the function is happening sort of quicker than real time on the first half, it could either happen quicker than real time on the second half and just try and dissipate to all those respective locations, or you would notice the difference between what happened on the first hemisphere and what happened on the second hemisphere. Not sure what that means. I'm gonna go and come back for a second. Okay, if I send you a picture of an atom with an electron spinning around it, then I tell you about an event that happens somewhere within the surface of the sphere. I say I disturb that electron at one point somewhere along its surface. Now, first of all, I can imagine that what that guy really wants to do is spin around the thing that I had in its way. Spinning is what it does. It's got to make a choice, which isn't arbitrary. It's based on the direction of the spin, which way it would spin around that obstruction. What's that good for? Well, all the electrons want to be spinning the same way with respect to that within an orbit, so that they clash the least amount of times. We want an electron at any given point to spin in the same direction no matter what it is. And once I had shown you this event anyway, and it's given some extra charge along some dimension of the orbital cloud, and so a part of it is going to be elongated. like nothing else around is elongated. And this elongation, with respect to other fields that we imagine as being just perfectly spherical around, is going to want to push this atom back to shape and make it perfectly spherical. Now this, it gets pushed by everything in all directions thing. Another way around to think of it is it's dissipating to this extra energy to everything that's close by to it. Whilst it's dissipating this extra energy to stuff that's close by it, we've got an electron that's running around and trying to find a circuit. And we've made this observation that if I've got just one side of the orbital sphere that I'm looking at, and I tell you there's one point of information here, there's one extra piece of charge, and this electron has got to still keep on spinning around, there's any point that it dissipates from that's on this side of the hemisphere. Wait. No. That is within half a hemisphere in either direction. So if it's anywhere, then I should be able to get information about, like, did we dissipate somewhere along this electronic orbital quicker than the time it would take for the electron to spin all the way around the circle. So it can be that this is why we see the thing in such perfect, vivid real-timeness, without any sort of granularity, that by the time any energy is moved, you already know where it's, like, all the maths has already been done. You poke the point here. Within the time it would take for an electron to travel through the whole circuit, you get information about that, let's say, as soon as you come to another point, which we're going to say is like an incident atom that you can release some charge to, or if you like, you've got a little bump on the edge of your circle and it's going to knock into this and get a little bit smoother. So when that happens, it doesn't take as long for that to happen as it takes for an electron just to spin around on its normal course. So if we're imagining all the energy, like heat and weight and all of these sorts of things, to resolve themselves by this similar method, we want to be just really careful about, it seems like they can do several things. Set several destinies in order for what this electron is going to do quicker than it can really go do it. That's okay, that's good. So we can imagine the amount of time it takes to allocate the dissipations, or to guess for that context, that spin of that orbital. Where is it going to meet dissipation points? Where is it going to meet bumpy points? And that working it out is free, because that's really just an intersection of other forces that are going on that we're about to compute when we say that at each dissipation point, from the moment of collision or excitement, as soon as the thing is there that it can dissipate to, finding out how to dissipate it doesn't take any energy, doesn't take any time. Doing the dissipation costs energy, costs time, always costs the same amount. And we've got a little gap between the two where potentially cool and exciting stuff could happen, where you thought you'd figured out what that electron was going to do, and something interfered with it along the way. And back to the intermediate axis theorem to wrap up, we had the general idea that the path that an irregular body is going to take is the one which has the best circle that puts the heaviest thing on the other side of the lightest thing, because you've got then the least heavy thing that you need to bring through an amount of space, and the most counterbalancing it can have. When the wingnut is flying around in space doing one kind of spin and then it flips, that's why it does that. Why does it flip again? It's because from its constant spinning, some of the electronic orbital paths are reinforced, or 2 dimensions of those are reinforced kind of everywhere, and that spinning of the spinning atoms, electrons, makes a little bit of extra effective weight down in that end, and then as soon as you've got a bit of extra effective weight down at that end that specifically isn't on the axis that you're spinning on but on the outside, then you've got a new intermediate axis, you've got this new apparent weight at the end of one side of the wingnut. And that's what we're going to use to try and explain how heavy stuff comes from electricity, and how light comes, can make everything. Maybe. This is the most specific picture we've had about where weight comes from, and it's also really close to the idea that I still haven't gotten around to of the Crookes radiometer computer. We'll get there. Okay, peace and love, thank you. Writing stuff in the book, thinking on the computer. You can see I feel close to dead. Look how pale I am. If I die, I'm so completely okay with it. I'm going to God. Peace.